discussing electric flux, and I gave you a homework question that if we have a spherical spherical surface, and at its center we have a charge Q like this. This radius is R. The question was, we need to find electric flux from this spherical surface using the concept of non-uniform electric field and flux associated with it. We find electric flux using phi, which is the integration of d phi. It's a good question for board examination, and therefore look at it carefully. What is d phi? D phi is E dot dA. In books you can also find ds for dA. Both are same, area vector. We use this format when electric field is non-uniform. This Q is a point charge. This Q is a point charge, then you know that it's electric field at different points. If I ask you what is electric field at this position, you will say that its magnitude is K Q divided by distance, which is R square. If I ask you what is electric field over here, then you will say again, it has same strength E. So it creates a confusion. People think that E is uniform. What is E? Look at the vector sign on top. So vector quantity. For a vector you have two things, magnitude and direction. At any point, each and every point of the sphere, if you go, you will find that strength, magnitude is what? Same. Because of same distance R. This is also R. You reach here, again, distance from the center is what? R. But directions are what? Different. And therefore, this E is not uniform. Because of it, we have to use E dot dA. Whenever electric field is non-uniform, you always go and find d phi in the form of E dot dA, and then only you investigate it further. Now regarding dA, let's talk about dA. What is dA? If you remember when I discussed that, whenever we go for area vector, and that too for closed surfaces. What is this? It's a closed spherical surface. It's a closed sphere. Sphere is what? It's a closed body. And for closed bodies, I told you that direction of area vector is always taken along the outward normal. So, for example, suppose somebody is at this point. At this point of the sphere, remember it's not a circle, it's a sphere. If you are at any point of the sphere and you choose a very small area, if I take a very small area, which I have shown like this, then its area vector will be perpendicular to it, not inwards but outwards like this. This is your dA vector, Similarly, if you go for electric field at the same point due to this charge Q, then this is our electric field is also in the same direction. E. That's your E. This is your dA. Both E and dA at this point, or if you are at this point, or if you are at this point, they are always parallel. At any point of the sphere, try to visualize the whole thing in this form. Just imagine, although this bottle is not a sphere, but I hope you can feel it. If for this bottle, you choose any point, which I can show like this. I hope you can see this black spot. This black spot on the surface, it represents dA, a very small area. Now, this is dA. You can take another dA. You can take another dA. And at different points, you can choose different dA vectors. They all are pointing perpendicular to the surface and away from the center. That's what I have shown in this figure. This is your E, this is your dA. Anywhere on the surface, if you go, you find that angle between E and dA is 0. Now, how do you open E dot dA? Magnitude of E. Now we will not use the arrow sign because we are interested in the magnitude part. Magnitude of dA into cos of angle between E and dA is what? 0. It's not about this point, it's about every point on the surface. Anywhere you go, angle is what? 0. Now, look at this carefully. You cannot take this E outside because it's a vector quantity and directions are not same, they are different. But you can always take this E out because this E is now the magnitude, and magnitude of electric field everywhere on the surface is what? Same. The moment you take it out, E, you are left inside with dA. Cos 0 is what? 1. What is dA? Area vector. What is this dA? This dA means, look at the black spot, this additional black spot which you see, its area is what? dA. This black spot, its area is what? dA. So these areas are dA, and I say that go for its integration for a closed sphere. For a closed sphere, if you go for the integration, then integration of dA will be A. It means what? You are taking sum of all these small dots which are present on the surface of a sphere. That area is what? A, and everybody knows now what's the value of E? KQ upon R square, KQ upon R square multiplied by A. What is surface area of a sphere? 4 pi R square. Now, this, what's the value of K? K is 1 upon 4 pi epsilon 0. 1 upon 4 pi epsilon 0. R square cancelled, multiplied by Q, multiplied by 4 pi. K is 1 upon 4 pi epsilon 0, 4 pi R square cancel. Now 4 pi and 4 pi cancel, and your final answer is coming Q upon epsilon 0. After some time, you will see that this whole thing is nothing but Gauss law. But right now we don't have to worry about Gauss. The question was, if you have a point charge, then electric flux produced by the point charge passing from a spherical surface of radius r, we are supposed to find that, and these are the steps which you need to follow. It's good example for board examinations, and therefore note down everything carefully. Note down this much. So write down these small things. So this E vector, the side note mentioned that E with vector sign is not uniform. E, the vector sign on top, is not uniform. So this is a hollow sphere, and it's not about hollow or solid. It's about the surface only. We find flux from a surface. When I gave you this question as homework, I told you that find out electric flux from the surface of a hollow sphere. Everything, when you go for flux, you have to worry about what? The surface. This surface area is what? 4 pi r square. Now, we're writing some point. Electric field, this one, is not uniform as its direction is different at different points. As its direction is different at different points. But E, write down E without an arrow, means only the magnitude part. But E represents magnitude, which is same everywhere on the surface. Which is same everywhere on the surface. Now let's understand, when we say that electric flux is number of electric field lines, what is the advantage of saying this? Look at this. We have been given a uniform electric field. When I say uniform electric field is represented by parallel lines with equal spacing. This type of E is uniform. Direction is same everywhere, and you know that density of electric field lines, it represents what? Magnitude. So it means everywhere strength is also same. We have a uniform electric field, and then we have been given a hemispherical surface like this. This is the hemispherical surface of radius r. This is the hemisphere. Our aim is to find electric flux associated with the hemispherical surface. It's not a closed surface, it's an open sphere which you have cut from the middle, giving you a hemisphere. So from the curved surface of the hemisphere, you need to find electric flux of this uniform electric field. Draw the figure and note down the question. Write down the question. Find out electric flux associated with the curved surface of a hemisphere of radius r. Corresponding to a uniform electric field E. Now give it 30-40 seconds. Let's see if you can yourself figure out what I'm asking you. Although it's not a hemisphere, but just imagine the way I've given you the question. Suppose this is the hemispherical part. I'm interested in the curved surface. Through this curved surface, electric field lines are coming from this side. This hemisphere is of radius r, and from the curved surface, we are interested in electric flux. Give it few seconds, maybe you can answer it. Look here. The kind of mistakes normally people commit. They go for phi. They simply remember phi as E into A. There is no concept of vector for them, and they simply write phi as what EA. They will be writing E as E, and the curved surface area. Curved surface area is what? 2 pi r square. It's curved portion. And then they will produce an answer like this, E multiplied by 2 pi r square, which is not correct. Now, proper presentation, proper way, I'll give you an idea how to investigate with the help of proper way, and then ultimately we'll be using the concept of number of electric field lines, which is called what? Electric flux. We'll be using this concept. The actual process is, you will do what? You will go for small dAs, the way we did in the previous question. You will find different dAs. This is dA. This is dA. This is dA. All these dAs are pointing in different directions. This electric field, that's your electric field E. That's your electric field E. That's your electric field E. That's how you will find the situation at every point of the hemispherical surface. Now, when I write E dot dA, I will have to calculate these, will have to take care of all these different angles. This angle is different. This angle is different between dA and E. This angle is different between dA and E. So if you go at different points, you will find that these angles are what? Different. Which means you need to perform integration. Somebody who is interested, try this integration. Once you try the integration, you will get the flux. But we will calculate that flux with the help of this concept. Look here. This is for those who are interested in integration. You can do that. But now look here. Question says, find out electric flux passing through the curved surface of the hemisphere. If we say that electric flux means number of electric field lines, then it means this. I'm just writing these 3 electric field lines. Any electric field line which passes from the blue shaded portion. Look at this blue shaded portion. Hopefully everybody can see it. Every electric field line which passes from the blue shaded portion will only pass from the curved surface. If I say that my hand represents the curved surface of the hemisphere, then any line which goes past this boundary, the opening, when it goes past it, it will definitely come out of it. I hope everybody can feel it. A line, if it enters the blue shaded portion, will definitely pass from the curved surface of the hemisphere. And therefore, instead of finding electric flux through the curved surface, we can simply find electric flux from the blue base, this blue base which you see. And it looks like this. We have the blue base, and your electric field lines are like this. These are your electric field lines. These are your electric field lines. And what about area vector of the blue portion? Remember, this curved portion, its area vector points in different directions. But for the blue portion, it's a flat portion, flat. Mouth opening of the curved surface, which is completely what? Flat. This thing. This portion is curved, but I am interested in this mouth opening, which is what? Completely flat part. From the flat part, for the flat part, this is what is the area vector. Electric field is what? Uniform. This E is uniform. We need flux. I will simply write E dot A. Electric field is uniform. You can always write E dot A, or you open it, magnitude of E, magnitude of A. What is A? This flat portion. What is its magnitude? I hope everybody can see. It's only pi r square. Curved portion is 2 pi r square, but this blue shaded portion, base, is only what? Pi r square. And what is the angle between these two? 0. That's the answer. Pi is coming E multiplied by pi r square. Put on this, make a cross. You cannot take 2 pi r square, because from the entire 2 pi r square, if you consider the curved portion, which is 2 pi r square, your angle between dA and E is not same everywhere. And therefore what we did, we used this concept of number of electric field lines. If somebody says that 3 lines enter through the blue portion, then these 3 lines only will cut or pass through the curved portion. So instead of finding flux from the curved portion, we will find it from the flat portion. Once you have the flat portion, your area vector is same everywhere. That is the advantage. If you understand this concept, then write down yes in the comment box and note down everything. Write down this point as electric flux means number of electric field lines instead of finding electric flux associated with the curved surface of hemisphere inside the bracket shown in black color, bracket close. We will find it for the flat base of the hemisphere. We will find it for the flat base of the hemisphere inside the bracket blue shaded portion shown in the figure. Next line. The advantage is for the flat portion. Direction of area vector is same. At every point. And in case they give you non-uniform electric field, but the same thing, then again do what? Find out a surface like this. Electric field is non-uniform, go for E dot D. But always try to convert your curved portion in this form. You can note down one more example on the same line. Suppose I replace the whole setup with a conical surface. We have been given that we have uniform electric field and a cone like this. It's a conical surface. They have given us radius of the cone as r, its height as h, slant edge as L. Uniform electric field. And the question is find out electric flux passing through the curved surface of the cone. So if somebody needs electric flux passing through the passing through the curved surface of the cone. Suppose we have a cone like this. And question says find out electric flux associated with the curved surface for an electric field which is uniform everywhere. If somebody goes for the area vector, then area vector its direction is different. But the trick is, instead of going for the curved surface, we'll simply say what? Those electric field lines which pass through the base of the cone. Now, how does it look? The base, it's what? A circle of area pi r square. Number of electric field lines which pass through the curved surface, these lines only will come out. And therefore, without wasting time in integration and all, we will again write what electric flux is E into pi r square. Note down this example also. There is no use of H, there is no use of L. You can answer the question simply with the help of R. Write down Gauss Law. Write down the statement of Gauss Law. Electric flux associated with a closed surface electric flux associated with a closed surface is proportional to algebraic sum of all the charges present inside the Gaussian surface. Present inside the closed surface. We'll also write it in the formal way, but look here. It's a closed surface. And from now onwards, we'll call it the Gaussian surface. Gaussian surface. What is the Gaussian surface? Closed surface. A sphere is a Gaussian surface, but this paper cup is not a Gaussian surface because this portion is open. It's not a Gaussian surface. Gaussian surface is something which is completely closed. There are several charges, some of them placed inside, some are outside. What Gauss says, electric flux associated with the whole thing, phi, is proportional to all the charges which are present inside, and take this sum with proper sign. When I say algebraic sum, it means with proper plus minus sign. This phi is proportional to Q1 plus Q2 minus Q3. Take them with polarity. Charges which are outside, you will not include them. These charges and these charges, we are interested in finding electric field, electric flux of all these charges. Remember, I said all these charges associated with the closed surface. Once we find it, it is only proportional to those which are inside. And you will get the visualization also in just a while. When you say that phi is proportional to this, ultimately this Gauss then becomes in this form. I'll simply write phi associated with closed surface is equal to Q inside the whole thing. Now in short, this is just for your understanding. This is a random example. This is Q inside. Now I'm removing the proportionality sign divided by epsilon 0. This is your Gauss law. Electric flux associated with a closed surface is equal to Q inside. What is Q inside? Algebraic sum of all the charges divided by epsilon 0. Put all this and then we'll write a few statements. First, note down everything in this form. Write down the statement. But first look here. Before you write the statement, let's also represent phi in this form. Suppose you are at this point. You took this point of the closed surface. This is the dA vector. And at this place, electric field is in this direction. This is dA, this is the electric field. Then, this part, phi, closed surface. How will you find it? You will find it with the help of E dot dA. That's how we find flux from any surface, whether open or closed. Remember, for any type of surface, whether it's open or closed, we always find flux with the help of E dot dA. But in Gauss, we always use what? Closed, just to show that we are using integration for a Gaussian surface. We use this symbol. Nothing special. This is the sign of integration. And this closed loop, it tells you that integration should be performed over a closed surface. This phi is nothing but this, which is equal to Q inside upon epsilon 0. Draw this E and dA also and this, and then we'll write statement. Saying that this phi closed, the formal way of representing phi is what? E dot dA. For any type of surface, whether it's an open surface or it's a closed surface, doesn't matter, you always write E dot dA. But in Gauss, we always use closed surface, and therefore we use this closed loop. This symbol simply says integration over a closed surface. Nothing special. Write down this and then we'll write some properties. First point, Q inside is only that charge. Q inside is only that charge which lies inside the Gaussian surface. Which lies inside the Gaussian surface. Remember, whenever I say Gaussian surface, it is always what? Closed surface. The second point, and before we write second point, let's see what do you think about it. I've written E. Whose electric field is this? This electric field E is due to the charges which are inside or due to charges which are outside, or is it because of every charge which is present inside or outside. What do you think? Write down in the comment box. Let me see if you know anything about Gauss, or you have your intuition, you can feel the things. What is your opinion? What do you think about this E? Whose electric field E is? If you think it's because of inside charges, then write down inside. If you think it's because of outside, then write down outside in the comment box. And if you think that it's because of all the charges which are present inside or outside, then simply write down all the charges inside or outside. Let's see, what do you think? Well, two answers are correct. It's not because of inside only, it's not because of outside only, it's because of each and every charge which is present inside or outside. And this is the beauty of Gauss law. You will understand the meaning of this thing once we handle some examples. Beauty is what? You're finding electric field of this, and all these. But on the right side, you're only taking what? These charges. How does it help us? You will see it once we handle some examples. But write down the property first, second point. Electric field E at any point on the Gaussian surface. Electric field E at any point on the Gaussian surface is due to each and every charge which is present inside or outside. Although we have written this point and I have told you this thing again and again, but just so that you do not commit any mistake, write down the third point also. Gauss law is valid only for closed surfaces. Gauss law is valid for closed surfaces only. Write down the fourth point. Although Gauss law is valid, for any type of closed surface, and for any type of charge distribution, it is useful only if we can find symmetrical electric fields for a given charge distribution. For a given charge distribution. You will understand meaning of this last statement in just a while. Now, first try to understand this Gauss law, and let's understand that why don't we count the charges which are present outside, and we will use the concept of number of electric field lines. This was Q4. Now, I told you that electric field lines, they represent what flux. Now, also remember this. Suppose we have a closed surface, can be any type of closed surface. For simplicity, I have drawn a spherical surface. If you have a charge inside, this is the charge, then these are the electric field lines. These are the electric field lines. And we are counting these electric field lines. That's kind of visualization. Otherwise, there is no number as such. I told you this. So we can always visualize electric flux in the form of number of electric field lines. We have this charge Q, and suppose this charge Q is producing 1, 2, 3, 4, 5 lines. 5 lines. We will say that electric flux in this case is 5. Very simple example. We say that electric flux is what? 5. Now, if I take the same surface, but if I place this charge Q somewhere here, not at the center, but close to the boundary. Close to the boundary. How do you draw electric field? Electric field will be drawn exactly in the same way. Programming, let's remove this Q4. This is your Q, and I'm drawing exactly the same type of electric field. Instead of placing charge Q at the center, we have placed the charge over here. What type of surface is it? It's a hypothetical surface. There is no real boundary. There is nothing which you can go and touch. This is just a hypothetical boundary. I told you that imagine a spherical Gaussian surface. You're not constructing any real thing. It's just a hypothetical boundary. So, if you place your charge here or you place your charge here, electric field lines, they will remain exactly in what? Same order. If I ask you what is flux, you will say what? Same number, 1, 2, 3, 4, 5. Gauss says what? Gauss says this is Q upon epsilon 0. Gauss says this is what? Q upon epsilon 0. It doesn't matter where this charge Q is. This charge Q is at the center, or is at this point, or is at this point. As long as it is inside, these 5 lines are only going to cut the Gaussian surface. That will be 5. This 5 is given by what? Q. If I increase the charge, I will simply increase what? Number of electric field lines. Because remember, number of electric field lines, it gives you what? Strength. So if you increase the charge, electric field strength will increase. That means its number will increase. Now, once I give you this visualization, and now look here. If I have my charge outside, if I keep my charge outside, then what is going to happen? This line, let's draw these random lines. These are the 5 lines. These are the 5 lines, and I am interested in electric flux associated with the closed surface. Now, this line is never going to cut it. This line is also never going to cut it. This line is also never going to cut it. So let's forget about these lines. Now, what is the meaning of electric flux? Electric flux, number of electric field lines that cut. Now, the cut is happening in 2 ways. Over here, line is exiting the surface. Line is exiting the surface, and at this place, line is entering the surface. What we say, the way counting is done, if it exits, we say plus, number wise, +1. If it exits, we'll say +1. If it enters, we'll say -1. If it enters, we'll say -1. That's how counting takes place. And the real reason behind plus and minus is because of area vector being along the outward normal. This is the electric field. If you go for area vector, then angle is what? 0 or acute, for which cos is positive. Listen again. For this line and for this line, area vector is this, outward normal. This is your electric field. The angle is 0. Cos 0 is what? 1. But now, over here, this is the electric field. But at this point, where is the area vector? Along the outward normal. Along the outward normal. That's your area vector. This is your electric field. What type of angle do you see? Obtuse. For obtuse angle, cos is what? Negative. And therefore, we say that when a line enters, give it -1. When it exits, give it +1. Which means, for these 2 lines, total count is coming what? 0. 1 + 1, 2, -1, -1, 0. That means, if you have a charge outside, its contribution in flux is what? 0. In this case, your flux is coming what? 0. In this case, they are only cutting once as they exit, and therefore you will simply say that flux is what? 5. Now, you place your charge here, anywhere, only 5 lines are going to cut. Only 5 lines. In this case, as long as you keep your charge outside, a line which enters will definitely exit. Entry -1, exit +1, and therefore these charges which are outside, they do not contribute in electric flux. Listen again, they do not contribute in electric flux, but their electric field, their contribution in electric field is present. If somebody wants to find electric field at this point, then electric field of this charge Q is definitely present at this point. Is also present at this point. At the point over here, electric field is present because of this charge. But from the overall closed surface, in electric flux, contribution is what? 0. If you understand this figure and these two, if you understand the logic, then write down yes in the comment box. If you do not, write down your doubt and I'll explain that again. This is the advantage of saying electric flux is number. As such, there is no number, but it helps us the whole process in visualizing electric flux. And with those points, you can also write an additional point, an extra point. Although that point is nothing but is included in the concept of area vector. For closed surface, we always take what? Area vector along the outward normal. So along the same line, write down the point. If an electric field line exits, if an electric field line exits a closed surface, it's counted as +1. And when it enters into a closed surface, it is counted as -1. I'll get this. With the help of this setup, I explained the logic of having only the charges present inside and removing all the charges outside. Why do we do that? Look, I'm not solving it. We'll solve these things in the next lecture. But right now, suppose you have been given an infinite line charge. This is called an infinite line charge. It's a wire of infinite length running from infinity to infinity. And what you have done, you have, just imagine you have posted charges at equal spacing. So this infinite charge, if they ask you find out its electric field over here, then we'll see in the next class. If we draw a surface like this. Why do we draw a surface like this? We'll see it in the next lecture, but right now, try to understand this part. It's an infinite wire, infinite line charge. Its electric field is required over here. And what we found that electric field is coming in this direction. This is the direction of electric field. With this electric field, we need to find its strength. What we did, we drew this Gaussian surface. This is called cylindrical Gaussian surface. Once we use phi, it will have the term of E and dA. E and dA means this E will be included. This E is present over here. What about the Q part? For Q part, we need to concentrate only on this portion. When we go for Q inside, we have to worry about this portion which is lying inside the cylindrical closed Gaussian surface. All these charges running up to infinity, their contribution in flux is 0. The contribution in flux is what? 0. But remember, the contribution in electric field is present. A charge like this, its electric field is present over here. Electric field of this charge is present over here. But it enters and then exits. And therefore we do not count this thing over here. But its contribution in electric field is present. This is the beauty. What is the beauty? Electric field is required of the entire charge distribution. But this Q is only this much. That's the beauty of Gauss Law. And we'll understand it better in the next lecture. You don't have to note down this. We'll see this part in the next class. Hopefully you understand the logic of Gauss and a few things. If you are still confused, just don't worry. These things will be clear once we solve examples like this. Every point of Gauss, when I say symmetrical, what is the meaning of symmetrical? What is the meaning of asymmetrical surface? These points and all, they will be clear in the next class. Hopefully you understand this much. Go down everything and then again leave. Thank you very much.